Alright, welcome to lesson 2.16. So here we're going to look at the polynomial identity that is by far the most important, and that's the binomial theorem. And it's incredibly important in calculus, in probability, in a lot of different real-world ramifications. So while we won't be looking at the calculus aspect of it yet, and we won't look at the probability aspect of it yet, talk a little bit about it, but not to the extent that you will be able to later on. No, this is still a very, very cool theorem from just a mathematical perspective. It can also be a little confusing at first, but that doesn't mean that it still won't make sense. It will. It's just that sometimes things will take a little bit longer. So stick with it. When you feel confused, know that that's what you would expect. I expect you to be confused. Don't get frustrated. Instead, just continue to work and have confidence that you'll be able to understand it if you put in the effort. So to start off, take a look at each of these binomials. Now, here's a little piece of new notation, but we've seen it over and over again. The term binomial, bi meaning two, nomial meaning number, and so a binomial is something that has two terms here. X plus 2 is a binomial. X plus 2 to the first power is a binomial to the first power. X plus 2 to the second power is x plus 2 squared. So x plus 2 times x plus 2, and each of these are considered a binomial. So go ahead and expand these out. All right, remember x plus 2 squared is x plus 2 times x plus 2. FOIL it out. Go ahead and do this on your own. And take note of anything that you're noticing, just any observation that you make. Okay, so hopefully the first four were pretty easy. X plus 2 to the 0 power is just 1. X plus 2 to the first power is just x plus 2. X plus 2 squared, you can FOIL this or do x plus 2 times x plus 2, and you get x squared plus 4x plus 4. And x plus 2 cubed is a little bit harder, right? Here what I would have to do is I'd have to do x plus 2 times x plus 2 times x plus 2. And so here we could multiply these two together, and then whatever we got from this, we would multiply by x plus 2. Okay? Now, when we get to x plus 2 to the 8th power, you're saying to yourself, oh my lord, I have x plus 2 times x plus 2 times x plus 2 times x plus 2. That's only halfway there. Times x plus 2 times x plus 2 times x plus 2 times x plus 2. Now, I am pretty sure that you do not want to spend the time to do this. And so a couple of things that you notice. First is, as the exponent gets bigger and bigger, the longer this process is going to take, right? Certainly, when I get to 8, I've already reached the point where I don't think it's a very good use of time to spend all this time multiplying these out. In fact, x plus 2 cubed took long enough. So my hope is there might be some way that for when I have a binomial raised to a power, I actually can just write down what the expansion is going to be by using the rules that it's following. So when I'm looking for a rule, looking for a theory as to what is actually happening, I can look to my examples here, noticing some of the patterns. Notice that the exponent here, 0, 1, 2, 3, that shows up in the first term, right? Because when I have, for example, x plus 2 squared, I'm going to end up with an x squared because I'll have an x times another x. And similarly, with x plus 2 cubed, I'll have x to the third power. Also notice that the last term is the last term in my binomial, so 2 to whatever power I have, 2 to the first. Here I have 2 squared because I'm going to have a 2 times a 2. And here I'll have 2 to the third power, or 8, because I'll have 2 times 2 times 2. So what we're noticing is, you know what, there might be some patterns that I can take advantage of, that I can actually say will work no matter what my exponent is, and no matter what the two things inside are, what the terms in the binomial are. And this is exactly the aim of the binomial theorem, to figure out a rule for any binomial raised to any power. What will the expansion look like? So let's go ahead and take a look at that now. Okay, so the rule that we're trying to figure out is what is the rule for taking a plus b and raising it to the nth power? What am I going to be getting whenever I do this? And this is for any binomial a plus b, and so what we need is to represent each of these possible terms with a variable, a and b, so that no matter what they are, we know what the rule is going to be and we can expand it. So to start off, let's take a look at the first few cases. Remember, when you're trying to prove something, when you're trying to show, and as we are here, right, what our end goal is, we're trying to say if you have a plus b to the n, that is exactly equal to something, and I want to show what this rule is going to be. What is it that a plus b to the n is equal to? So what I'm going to do is I'm going to start off looking at what happens when I do a plus b to a fairly simple power, right? 0, 1, 2, 3, 4. Let's go ahead and start out with a plus b to the 0. Now, I would like to write this out and really clearly show what is a plus b to the 0. Well, that's just a plus b to the 0. There's nothing really to write out, and whenever I raise something to the 0, I end up with 1. So that's just going to be equal to 1. Notice I'm giving myself plenty of space over here. All right, what about a plus b to the first power? Well, again, this is pretty simple. I'm just going to end up with a plus b because I'm raising it to the first power. Okay, what about a plus b squared? Well, here, remember, this is a plus b times a plus b. A plus b times a plus b, right? So what is this going to be equal to? Well, I multiply it out, and what I have to do is I have to take a, and I can't just multiply it by a. I have to take this first term, and I have to multiply it by both pieces here, okay? So I have to do a times a and a times b. And then I have to take b and multiply by both terms here, so I'll have b times a, which will be another ab, and then b times b, which will be b squared. So I'll have a squared then I'm going to have a times b and another a times b, meaning I'll have 2 of those a times b values. And last, I'll have b times b, which will be b squared. Okay, what about a plus b cubed? Well, notice this is just a plus b times a plus b times a plus b. I'll write that down below. A plus b times a plus b times a plus b. Well, this seems kind of tricky because I'd have to look at all the possible combinations. I'd have to take a, and I have to multiply it out, not just by both a and b here, but I have to do a times a, and then times a, and then I have to do a times a, and then times b. I have to look at all the possible combinations because the distributive property tells me I have to multiply a by all of the other pieces in each other binomial. That looks like kind of a pain. But notice that a plus b times a plus b, that's just a plus b squared, and I've already done that. So I can just take whatever this is and multiply it by a plus b. And the distributive property makes this a little easier. I'll have a times a, that'll give me an a cubed. I'll have a times 2ab, and that'll give me 2a squared b. And then I'll have a times b squared, and that'll be a b squared. And then I'll do b times each of these. I'll have b times a squared. Okay, and I'll have b times 2ab, and that'll give me 2ab squared. Well, notice I had an ab squared already, so I'd now have 3 ab squareds. Then I'll do b times b squared, and I'll get b cubed. So what am I going to end up with? Well, first I'm going to have an a cubed. Okay. Then remember I got 2 a squared b's, and I had another b times a squared, which would be 1 more a squared b. So I'll have 3 total a squared b. Okay, now notice I also had an a times a b squared, and I had 2 ab squareds. So that's going to give me another 3. And this time I just have an a to the first and a b squared. And last but not least, I had b times b squared, which was just b cubed. All right, what about a plus b to the fourth? Well, same idea here, right? Here, this is going to be a plus b times a plus b times a plus b times a plus b. Well, this looks like a real pain because I'd have to look at all the possible combinations. I'd have to say, okay, well, first I could have all a's. I could multiply all the a's together. But then I could also have all these combinations where I had an a, another a, another a, and one b. 3 a's and one b. In other words, I'd have a cubed b. But notice there's more than one way I can do that. Because I do a times a times a times b. But I could also do b times a times a times a. And that's just going to get really, really long and laborious. But notice that this is a plus b times a plus b times a plus b. That's what we just did up here. So we can actually multiply through, we can do a times all of these, and then b times all of these, and add the like terms together. So go ahead and do that off to the side. So leave this space empty, and do a times a plus b, and distribute each a and b into this, multiply them through, and add the like terms. All right, first we ended up with an a to the fourth power. Okay? And then we had an a to the third power times a b to the first power. How many of those did we have? Well, certainly we had an 3a to the third times b. That would be 3 of them. But then when we multiplied b by a to the third, we got b, a to the third, or a to the third times b, and that would be another one of those terms. So I'd have 1 plus 3, which would be 4. Okay. Then I had a squared times b squared. How many of those did I have? Well, when I multiplied a by 3ab squared, I got 3a squared b squared. And when I multiplied b by 3a squared b, I got another 3a squared b squared. So I ended up with 6a squared b squareds. Okay, what happened next? Well, I had a times b cubed. That gave me an ab cubed. When I multiplied b by 3ab squared, I got 3ab cubes. So I got 1 and 3, and I add those together, and I ended up with 4a times b cubed. And then last but not least, I had b times b cubed, and that multiplied together to be b to the fourth. And so then I was all done. Now what I want to notice is the pattern that I'm continuing to see. So what I want you to do, and to come in tomorrow ready to talk about, is what are the patterns that you're noticing? And I'll give you a couple of things to look at, and your goal is to write down. So here's what you need to do. You need to write down 3 patterns that you notice. 3 patterns that you notice. List them, 1, 2, and 3. And after you've noticed those patterns, you're going to try and write out what a plus b to the nth power should be. Now, if you find that really challenging, that's okay. What I then want you to do is take it a step back. Try a plus b to the 5th. And try using your patterns that you noticed to write out a plus b to the 5th. I'm going to give you a couple of tips. Remember, you have to look for 3 patterns. Here are some places to look. Look at what's happening to the power of the first term, a, as you move to the right. What's happening to that power? Also notice what's happening to the power of your second term, b, as you move from the left to the right. Okay? Then the next thing to look at is how do the coefficients relate as I go from a plus b to the 0, a plus b to the 1, on down. And here's where I'm going to make it a little easier. Notice the coefficient of a is 1. Coefficient of b is 1. 1, 1, 1, 1, 1, 1. Then look at the inside ones and notice how the inside ones relate to the 2 above it. All right, so I've given you a couple of hints. Try and write down the 3 patterns and use them to write out a plus b to the 5th, and then as a final piece, try and write out a plus b to the n.